Okay, let's unpack this. Our mission today is a deep dive into how large models learn after their initial training, specifically comparing supervised fine-tuning SFT with reinforcement learning or RL. We really want to separate, just memorizing data from actually learning principles that, well, generalize.
Exactly. And we're looking at this through the lens of some specific research. It uses rule-based reasoning tasks. There are two main environments. General points, that's an arithmetic card game with text and vision versions, and VIRL, which involves real-world spatial navigation, also with text and vision variants.
Right. So the core question is pretty clear. Which method, SFT or RL, actually helps the model generalize when faced with, say, new rules or different visual inputs? Does it learn the rule or just the examples?
And the findings are, well, quite stark. RL shows consistently better generalization, particularly when it's trained with an outcome-based reward. Does it achieve the goal? It generalizes across both new text rules and visual variations.
Whereas SFT seems to get stuck.
Very much so. SFT tends to overfit to the training data it sees, it memorizes. This leads to really poor performance when you take it out of distribution, Odo. For instance, in that VRRL task, just changing the text rule slightly caused SFT performance to absolutely plummet by nearly 80%.
Wow, 79.5%. That's not just poor performance, that's basically failure when encountering novelty. It makes sense if it's just pattern matching the training examples.
Precisely. It's learning the specific sequence, not the underlying logic.
And does this hold up when the novelty is visual, not just textual, like different looking cards or navigating completely new city layouts?
Yes, the pattern holds. We see the same contrast in visual ode tasks. Take the VIRL mini benchmark. RL pushed the success rate up by a massive 33.8 points from 44% right up to nearly 78%.
So it's handling visual variations much better too. Why is that? Is it just applying the learn-to-text rules more robustly?
Well, the analysis suggests something deeper is happening. It seems the RL process actually improves the model's basic visual recognition abilities. The reward signal is refining how the model sees and interprets the visual input, making it inherently more robust to visual changes. That directly helps generalization.
That's fascinating. So RL isn't just a high-level policy tuner. It's potentially reaching down and improving core perception capabilities. But, okay, even with RL being the star for generalization, the research also says we can't just ditch SFT, right?
Absolutely not. SFT plays a critical foundational role. It's like the format teacher. It stabilizes the output format. Without SFT first, trying to apply RL directly to the base model, like the LLaMA 3.2 vision model they used, just doesn't work well.
Why not?
The base model isn't great at following instructions yet. It produces long, unstructured, kind of rambling outputs. RL needs a coherent structure to evaluate and improve upon. SFT provides that initial structure and instruction following ability.
Okay, so SFT preps the model, makes it follow instructions and output things in a useful format. Then RL comes in and teaches it to generalize based on outcomes.
Exactly. And this hybrid SFT then RL approach enables something really interesting with compute at inference time.
Ah, the scaling aspect.
Yeah.
Using that multi-turn RL framework.
Precisely. It uses sequential revision. Basically, the model can check its own work, iterate, and refine its answer over several steps. This means you can actually trade more computation time at inference for better generalization.
And there's data showing this works.
Yes. They found that increasing the number of these verification or revision steps significantly boosts ODE performance. For example, in the general points text task, using 10 steps improved ODE generalization by almost 6%, whereas just one step barely moved the needle, less than 0.5% improvement.
So more thinking time, more self-correction leads to better application of the learned principles.
It seems so. That iterative refinement appears key for tackling these complex, multimodal generalization challenges.
Okay, so summing this up, RL seems to be the powerhouse for acquiring generalizable knowledge, especially across modalities and rule changes. But, and it's a big but, it needs that initial scaffolding provided by FFT to get the format and basic instruction following right.
That's the main takeaway. SFT sets the stage, RL learns the general principles, but this leads to a really interesting practical question. The research notes that RL doesn't work well if the SFT checkpoint is too basic or too overfitted.
Kind of a Goldilocks problem for SFT.
Exactly. You need it tuned just right. So the provocative thought here is, how do we precisely define and achieve that optimal SFT state? How much SFT is enough to enable RL effectively without accidentally baking in too much memorization that hinders the very generalization we want RL to achieve? That seems like a crucial calibration challenge for building truly adaptable models.